Okay, so picking up with DNF, disjunctive normal form, as I said, it's another representation for Boolean functions, a lot like what we were looking at last week. So we can have a literal, which is a clause, which is just the letter straight, or we can have the negation of a clause where instead of using that little broken minus sign for not, we're now using an overstrike bar, right? So a bar over. So those two things would be read as A and not A. We can have terms, and terms are sets of literals that are connected by a logical and we represent an and by adjacency, or simply by putting the two literals together. So last week, where we were looking at A and B with this, A, a arrow kind of sign, B, this week in DNF, we're going to be representing that as simply AB. And where we had not A and B, now it's just not AB. So the fact that those two clauses, those two literals are together like that, that indicates and. Now terms, you will often see that terms are also called implicants, because if a single term is true, then it implies that the entire predicate is true. And why is that? It's because a predicate is a set of terms that are connected by or. And here, or is indicated by the plus sign. So for example, last week when we might have had A or with this little V symbol B, now to us that now looks like this A plus B, although we would still read it as A or B. And I know this is a little confusing because you look at that plus sign and you kind of want to think that means A and B, but that plus sign indicates or in this notation. So when we're using DNF, there are 9 different basic categories of faults that we could have in DNF. And we'd like to have some test criteria that will guarantee that if we satisfy the test criteria, we're guaranteed to find faults of this type. So we can have expression negation faults, where we're taking the whole predicate and we're negating it. So if we intended to have F equals A, B, or C, or A and B or C, our faulty expression would be the negation of that whole thing. We can have term negation faults where we're doing a not on a single term. We can have a literal negation fault. I skipped one where we're negating just one. And here, this is A, not B, or C. And for some reason that I don't understand, when I look at this outside of slide view mode, this shows up as a whole bar over B, but in the slide view mode, it just kind of shows up as a little dot. Not sure what's going on there, but that is not B. There's supposed to be a bar there. So we have these 9 different types of, 9 different classes of faults. And as I said, we'd like to find test criterion such that if we satisfy the criterion, we're guaranteed that we would find all errors of all of these kinds of faults. Now, it turns out that these fault classes have a subsumption relationship of their own. So if I can find all literal insertion faults, then that guarantees that I can find all literal reference faults and all term omission faults and literal negation faults and operator reference faults, right, so on down the subsumption tree. So I really only need to be able to find 2 kinds of faults. If I can find literal insertion faults over here, and I can find literal omission faults over here, then that guarantees that I can find all of the different faults. So those are the things that we'd like to target. So when we think about our DNF representation and what kind of coverage criteria can we have for this? One criterion that kind of comes to mind immediately is, okay, so if I've got a predicate that's made up of these implicants or terms, then maybe I should check to see, I should have test criteria to make each implicant evaluate to true. So of course, because each implicant, if any implicant evaluates to true, then the predicate evaluates to true. All right, and that's the case because the implicants or terms are strung together with ORs, right? So if any one of them is true, then ORing it with all the other ones will make the whole predicate true. So to be a little more thorough, what we'll do is we'll check all of the implicants for some predicate F, and then we'll also check the implicants for the negation of that predicate. And so we should have test requirements for the predicate and the negation of the predicate, test requirements that each implicant should evaluate to true. So if I look at, let's see, how can I, where's my pointer here? Oh, it's not going to give it to me. All right. If I have a predicate F that's A, B, or B not C, I can negate that whole predicate. For the moment, don't worry about how I negated it. Take my word for it. We'll come back to how to negate these predicates. But if I negate that predicate to get not F, then not F is equal to not B or not A and C. And so I can put together my collection of implicants, right? My set of implicants for F and not F is AB, B not C, not B, and not AC. And so now I can put together some possible test sets so that I'm setting each one of those predicates, each one of those implicants to be true. So if I have true, true, false in the order of A, B, and C, of course, then true, true, false as a test set, that satisfies AB because A is true and B is true. And it satisfies B not C because B is true and C is false. It doesn't satisfy not B and it doesn't satisfy not AC, so I need another test set. But if I add the test set false, false, true, then that satisfies not B because B is false, and it satisfies not A, C because A is false and C is true. So those two test cases for A, B, C will satisfy checking that whole collection of implicants are evaluated to true. Now, it turns out that implicant coverage isn't really all that useful. It's a fairly weak test criterion, and it doesn't end up guaranteeing that we find any of those DNF fault classes that we were looking at on the previous slide. So while we can certainly use it to generate test cases, we can't use it to guarantee that we found any of those types of problems. So we need some better coverage criteria than that. So let's look at what we can do to improve on implicant coverage. And to do that, we first need a few more definitions because we always need more definitions. The first definition is a proper subterm. And proper subterm, this is very analogous to a proper subset. A proper subterm is a term that we've then taken one or more clauses out of. So if we start with term ABC, then ABC has proper subterms A or B or C or AB or AC or BC, but not ABC because ABC is not a proper subterm of ABC. We can then have the notion of a prime implicant. And a prime implicant is an implicant or term such that no proper subterm of that term is also an implicant. So if we have this predicate F equals AB or A not BC, AB is a prime implicant, but A not BC isn't a prime implicant. Why not? Because we can simplify this to AB or AC. So its proper subterm AC is an implicant. Okay, so that was easy for me to say, and you're probably thinking, okay, it's not at all clear to me how A, B, or A not BC gets simplified. However, in the upcoming slide, we're going to go over how to simplify. But a prime implicant is one such that there are no proper subterms that are also an implicant, right? We can't simplify that term any further. And the kind of opposite notion of that is a redundant implicant. A redundant implicant is one that I can remove completely without changing the value of the predicate. So if I have F equals AB or AC or B not C, implicant AB is redundant because I can simplify this whole predicate to AC or B not C. And again, we'll see in a minute how we actually do that simplification. All right, we're going to see right here. So we are going to be using Carnot maps or K-maps to simplify our DNF predicates. So if we have F equals AB or AC or B not C, the example from the previous slide, we can use a K-map to simplify this. And so when we make a K-map, hopefully you've had exposure to Carnot maps before. I'm not going to go into them in a whole lot of depth, but I will go through a brief explanation here, and I think you'll probably, even if you haven't had exposure before, I think you'll probably be able to catch on to this pretty quickly. They are fairly straightforward. So I'm going to take this predicate and I'm going to represent it in a Carnot map. And here's the Carnot map. And what's in here? Well, we're grouping a pair of clauses, or one pair of clauses and a single clause here, because here we have three clauses, A, B, and C. So we're going to group A, B together and put them on the x-axis of the map. And then we're going to take the remaining clause, C, we're going to put it on the y-axis of the map. And then we're going to label each of the rows and columns. But the key thing here is we're labeling these using what's called a gray code. And a gray code is one where with every step, we're making only a single bit or a single digit or a single true false value change. So you'll note that this is not binary counting. We're not 0, 0, 0, 1, 1, 0, 1, 1. Instead, we're changing only one truth value at a time. So we're going false, 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 true, 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 false. So we've cycled through all of them, but we're changing only one at a time. And then we're going to go into the body of the K-map, right into the matrix here, and we're going to populate this truth table where any cell that's true, any combination of truth values that's true, we're going to denote with a T in the map, and anything that's false, we are by convention going to just leave blank. So if we look at what each of these terms contributes to the Carnot map, we see, okay, we've got the term AB. So we want to find the cells in the K-map where A is true and B is true, and that's this third column right here, the highlighted column. That's where A is true and B is true. And so we're going to mark those true in the K-map. Then we're going to look at term AC. And so we want to find cells in the table, cells in the Carnot map, where A is true and C is true. That's these blue cells. Then we're going to look at term B not C, and we're going to find cells in the table where B is true and C is false. And that gives us our entire Carnot map. And now we can use that Carnot map to simplify our predicate. And the way we're going to simplify our predicate is we're going to search in the Carnot map for rectangles. Okay, rectangles in the Carnot map that are 2 to the m by 2 to the n, right? Powers of 2 in size. So 1 by 1, 1 by 2, 2 by 2, 2 by 4, 4 by 4. We're going to be looking for powers of 2 rectangles that are sized as big as we can make them, right? The largest possible rectangle we can make that contains true values. So for example, I will select from the Carnot map these two here that are in blue. And that's as big a rectangle as I can make. I can't expand that in any other direction while keeping it containing only true values. And so what does that map to as far as the predicate goes? What does that mean as a term? Well, I can see that for the cells that are blue, A is always true and C is always true. So the term that matches that rectangle is AC. And if I look at the remaining cells, these red ones, okay, I can see here that B is always true and C is always false. So those cells can be represented by B not C. And that's how we've simplified AB or AC or B not C into AC or B not C. So we dropped out AB. Why did we drop out AB? Well, AB is right here, right? AB is right here in this column. We dropped it out because we didn't need it, because those cells were completely captured already by the other two terms that we had. So one key thing about Carnot maps. Carnot maps are a torus. They're not a plane. The left side of the Carnot map wraps around to the right side, the top wraps around to the bottom, and vice versa. So if you took this color-coded K-map and really wanted to look at it in 3 dimensions, you'd really come out with this donut-shaped torus. So I see a question on the chat about 3 variables. There's actually nothing magical about 3 variables. You can do a Carnot map with 2 variables, you can do it with 3, you can do it with 4. When you get past 4, you can still do it, but you have to actually start making multiple copies of it, because on paper we can't really do a nice 3rd dimension, right? We could do, let's see, how many? I guess if we're going to go to a 3rd dimension, I suppose we could support 6 variables, I think. But usually it starts to become inconvenient after 4, because you have to start making basically stacks of them to represent that third dimension. So if we have this predicate, and here I'm ignoring AB for the moment, I'm just going to focus on AC. I'm going to focus on not B, not D. And so if we have not B, not D, then that maps to these 4 cells. The key thought here is that those 4 true values, they are a single rectangle, right? They are a single 2 by 2 rectangle, because the top wraps to the bottom and the bottom wraps to the top. So we always want to be paying attention to wrapping around the edges. When we're trying to maximize the size of our rectangle, we want to always be thinking about whether there's an edge that we can wrap around to capture more cells. So let's look at some prime implicants. If we've got this nasty predicate, F equals ABC, or AB not D, or not A, B, C, D, or A not B, C not D, or A not C not D. Okay, let's draw the K-map. So we'll go term by term. Say, okay, A, B, C, that's where A is true, and B is true, and C is true, and we don't care about D. So that maps to those 2 cells. And A, B, not D, all right, A is true, B is true, D is false, and we don't care about C. Or not A, B, C, D, so A is false, B, C, and D are true. A not B, C not D. And A not C not D. So we've used all these terms, we've built up our Carnot map. Now let's figure out what the prime implicants are and what the simplified form is. So which of these are not prime implicants? Well, AB not D is not a prime implicant, right? AB not D was, let's see, AB not D, that was blue. That was that up at the top? Yeah, okay, so that's these 2 guys. So if we come here, AB not D is here and here. That's not a prime implicant, because it's part of the bigger rectangle A not D, which is this outlined in blue rectangle, 2 cells down here, 2 cells up here. If we look at not A, B, C, D, that's this red or pink cell here. That's not a prime implicant, because it's part of a bigger rectangle, BCD, this red rectangle. If we look at A not B, C not D, that was A not B, C not D, that was this corner. That's not a prime implicant, because it's part of this bigger 2 by 2 blue rectangle. And A not C not D, A not C not D, that's these 2 up here. That's not a prime implicant, because it's also part of this larger 2 by 2 rectangle that's outlined in blue. So all of those have proper subterms that are implicants. And so if we do our simplification, which I've kind of given away by now, our minimal simplification, our minimal representation that has just prime implicants is A not D, and that gives us this 2 by 2 blue, and BCD, which gives us this 1 by 2 rectangle in red. Okay, so when we're looking at the minimal representation. Okay, I kind of talked about this on the previous slide. The minimal representation is just just working out the maximum size rectangles and finding what that solution is. So same example as on the last slide. If we went with this long predicate here and filled in all the individual true values, we can find our maximally sized rectangles and come out to A not D or BCD. So last week we talked a lot about when a clause determines the predicate. And we did that two ways, right? We used our XOR approach, and we also looked at our truth tables and did kind of a visual examination of the truth tables to determine what are the conditions under which any particular clause determines the predicate. Well, we can also use Carnot maps for that. So let's say we've got this predicate B or not A, not C, or AC. So we've got B, that fills in these four, right? That's everywhere where B is true. Not C, not A, not C, fills in over here. AC fills in over here. So we've built up our Carnot map. Now let's say we want to identify what are the conditions under which B determines this predicate F. Well, first we'll draw some lines, right? We'll identify the boundaries where the value of B changes. And so here, as we skirt across this first line, B changes from false to true. And as we move across this line, B changes from true to false. So these two lines indicate the places where B changes. And now let's look for cells on either side of that boundary where F has different values. And we can find them right here in this upper space here. We've got adjacent cells on either side of the boundary where the predicate turns from true to false. And here the predicate turns from false to true. So these are the conditions under which B determines the predicate. And if we now look at that and reduce that to its own conditions, we can see that B determines the predicate for A not C, right, which is these two cells here, and not AC, these two cells here. So those are the conditions where B determines the predicate. Now, if we took this predicate, rephrased it in the notation we used last week, went through our XOR approach, or built up our truth table and did it that way, we would get the exact same answer. So just another representation and another method to basically do the same thing. So I mentioned earlier when we were talking about implicant coverage that we were taking the predicate F and the negation of the predicate not F. And I kind of asked you to trust me when I gave you that big predicate and said, okay, and here's the negation of it. Now we know enough to figure out how we can easily negate the predicate. So let's take A, B, or BC. Let's build a Carnot map. All right, so we've got AB in the yellow or BC in the blue. And now we want to negate that into not F. So basically, we just redraw the Carnot map and we negate all of the cells, right? Any cell that was true becomes false, any cell that was false becomes true, and now we have the Carnot map for not F. And now we can identify our maximally sized rectangles and extract from this what the DNF predicate is for not F. So what do we have here? We have not B, right? Because these four cells, because recall, the Carnot map wraps around left side to right side. So these two cells, these red areas make up a single 2x2 cell, or not A, not C. Now here's a little thing that I want to point out. If we look at what we got, the cells that we captured with not B, the only thing left is not A, B, not C, right? This is the only cell in the Carnot map that hasn't been captured yet. And so it would be tempting to write this predicate, the predicate not F. It would be tempting to write it as not B or not A, B, not C. However, that would be an incorrect thing to do because identifying that one cell is not the maximally sized rectangle that we're able to build that contains that one cell. The maximally sized rectangle we can build is this green rectangle, which is not A, not C. And so we're always trying to make our rectangles as big as possible. The reason we're trying to make our rectangles as big as possible is because the bigger the rectangle is, the smaller the term is. And so we're trying to get our most simplified term. So if we had B in here, right, not A, B, not C, well, we could simplify that to not A, not C, right? And then we have a simpler predicate. So that's why we're always trying to maximize the size of the cells that we're using, or maximize the size of the rectangles that we're identifying in the Carnot. And it is okay that this part, right, that this term also includes cells that were part of some other term. That's okay.
Professor, previous slide.
Yes.
Isn't the result F bar?
Down here in the bottom. Yes.
Yeah.
Yes, this is not F. Yes.
Okay.
Yep. It is. Thank you. I'm not sure if that's a slide error or whether it, for whatever reason, didn't want to show up again like I had that earlier example, but I'll check that out and fix it if I can. Thank you. Okay, so now in our Carnot map, we can also kind of derive this idea of true points and false points. True and false points, this is pretty obvious. If we look at this predicate, F equals AB or CD, we can build our Carnot map, right? AB gives us this column, CD gives us that column, or that row rather. So let me take an aside for a moment because there's an interesting thing that I want to point out that I think can be a useful sanity check for you. Every time you add another literal to your term, you cut the number of true cells in half. So for example, if I had this 4x4 Carnot map that included A, B, and C, D, and I had a term that just said A, of those 16 cells in the map, a single term would give me half of those cells true, right? It would give me, if I asked for A, it would give me the third column and the fourth column. So half the cells would be true. If I add another term and add another literal and make my term AB, it cuts the number of true cells in half again. So now AB gave me 4 true cells. If I added another literal and used ABC, it cuts it in half again, and that would give me 2 cells. And if I used ABCD, then that would give me only 1 cell. So every time you add another literal into your term, you're cutting in half the number of cells in the Carnot map that term affects. So that's just an interesting little tidbit to have, because then you can start to look at this and say, oh, I have A not B, C not D. And you can immediately say, oh, well, it has all 4 terms in that, so therefore that's only going to affect 1 cell. And it's a nice little sanity check that you're actually doing the right thing. All right, so we have A, B, or C, D. And then this is going to allow us to identify the true points in this Carnot map. And the true points in the map, the ones that are identified in the little blue boxes here, okay, this is really simple. The true points are simply the cells in the map where the value is true, where the value of the predicate is true. Guess what the false points are? It's all the cells on the map where the value of the predicate is false. So true points and false points, not really all that interesting, but it sets us up for something that is interesting, and that's unique true points. So a unique true point, or a UTP, with respect to some particular implicant, is a set of truth values such that the given implicant is true, and all other implicants are false, meaning that this implicant and only this implicant is the one that caused a unique true point to be true. And so that unique true point focuses any testing on a particular implicant. So let's take a look at that again. We're going to go back to our A, B, or C, D example. So if I look at implicant AB, what are my unique true points for AB? Well, those are the points that AB caused to be true and that no other implicant caused to be true. So true, true, false, false, that's a unique true point for AB. True, true, false, true is a unique true point for AB. True, 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 true is a true point, but it's not a unique true point for AB because CD also caused that to be true. So that's why it's not a unique true point. And true, true, false, true, 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 false here at the bottom, that is also a unique true point because AB caused that to be true and no other implicant caused it to be true. Now, if I look at the unique true points for CD, I get something analogous, right? False, false, true, true, false, true, 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 false, true, true are all the unique true points for CD, but not true, 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 because while it's a true point, it's not unique to CD. So that leads us to an interesting test criterion. Minimal unique true point coverage, or MUTP. As we get further and further into this, the names get weirder and weirder. But I didn't make them up, so I'm not taking the credit for that or the blame. So multiple unique true point coverage. We first want to have a minimal representation of our predicate, and a minimal representation guarantees that there's at least one unique true point for each implicant. Because if there were no unique true points for an implicant, then it's not a prime implicant and it can be simplified further. So in multiple unique true point coverage, we have a requirement that for each implicant in the predicate, we want to choose unique true points so that the clauses not in the implicant are true and false. So let's take a look at that. So we want to choose unique true points for each implicant so that the clauses or the literals that aren't in that implicant take on values true and false. So if we look first at implicant AB, let's take a look at AB, and we want to find unique true points for AB such that literals that aren't in AB, which means C and D, take on values that are true and false. So we could pick these two cells, right? We could pick this unique true point where C is false and D is true, and this unique true point where C is true and D is false. So we've satisfied MUTP for AB because we picked unique true points for AB, and the literals that aren't in AB, namely C and D, appear in both true and false values. Then for implicant CD, we could choose false, true, 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 and true, false, true, true. And again, these are unique true points for CD where the literals that aren't in CD, namely A and B, take on both true and false values. So here A is false and here A is true. Here B is true and here B is false. So A and B have taken on different values. And that leads us to our MUTP test set, right? So these 4 points, true, true, false, true, 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 false, false, true, 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 false, true, true. That becomes our test set that satisfies multiple unique true point coverage. Multiple unique true point coverage seems clever, seems great. It does have a problem with infeasibility. So if we consider this predicate, A, B, or B not C, we've simplified this as much as we can, right? This is a prime representation. There's nothing we can do to simplify it further. Our implicants are A, B in the blue and B not C in the red. Both implicants are prime. Neither implicant is redundant. We've done everything we can. We've got a nice predicate here, but we've got a problem. If we look at the unique true points for AB, the unique true point for AB is true, true, true. Right? This is the unique true point for AB. This is another true point, but it's not unique because both implicants cause that to be true. So here, true, 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 true is the only unique true point for AB. So can I find unique true points where C is true and is false? Well, even without looking at it very far, if I've only got one unique true point, I can't cause anything else to be different, right? So MUT-P is infeasible in this case for AB because I have found a unique true point where C is true, but I can't find a unique true point where C is false. So MUT-P is infeasible. And if I look at B not C here in the red, I can find a unique true point. That would be false, true, false. That causes B not C to be true, right? And it's a unique true point. And at that point, A is false, but I can't find another unique true point where A is true. There is no other unique true point for B not C. Therefore, again, B not C, MUT-P is infeasible for this case, for this predicate. So what does MUT-P give us? If we go back to our chart of the things we'd like to satisfy, well, it turns out MUT-P is very powerful because multiple unique true point coverage, when it's feasible, it will find all possible literal insertion faults. And if it finds all possible literal insertion faults, then we know it will find all these other faults as well. So really what we'd like next is a way to find all literal omission faults. And if we find all the literal omission faults, we'll also find the operator reference faults and we'll be done. So let's look at how we might find literal omission faults. And that takes us to near false points. So a near false point, or an NFP, with respect to some clause, right, some literal in an implicant, is an assignment of truth values such that the predicate itself is false. But if we change the particular clause or literal that we're looking at and leave everything else unchanged, then the implicant and thus the predicate changes to true. So at a near false point, that literal C determines the predicate. So we have kind of a nasty name here, corresponding unique true point and near false point pair coverage. Yeah, cut P and FP. So given a minimal DNF representation, we want to go through each clause in each implicant and find a unique true point and a near false point. Let's take a look at an example. We're going to go back to A, B, or CD. We understand A, B, or CD pretty well by now. So what's our process? We're going to take each implicant or each clause, and we're going to find a unique true point and a near false point. So for A in AB, we first want to find a unique true point. So a unique true point could be true, true, false, false. And a near false point would be taking that unique true point and just changing A from true to false. So that'll take us over here. That's our near false point, our corresponding near false point. False, true, false, false. Or we could pick this pair, or we could pick this pair. In each case, we've picked a unique true point for the term, the implicant that A is part of, and then we've changed A from true to false to get us a near false, a corresponding near false point. So we could have picked any one of those pairs. And if we look at clause B in AB, then again, we need to pick unique true points and near false points. And again, the unique true points are easy. It's going to be the same set of points. But now we want to take the unique true point and we want to change B from true to false and find that corresponding false point with respect to B. So we can get true, true, false, false for the true point and true, false, false, false for the near false point. And likewise, we could pick each of the other unique true points and derive a near false point from it. So where do we then select? Well, we need to select a unique true point and near false points. Which ones do we select? Well, we could pick any one of the first pairs and any one of the second pairs. But if we want to reduce our test cases, which always seems like a smart thing to do, we should probably pick ones where the unique true point matches. Because if I pick true, true, false, true, and false, true, false, true, and true, true, false, true, and true, false, false, true, I've reused the unique true point. So it saves me from having to write another test. So instead of having 4 different tests, right, I now have 3 tests because I reused the unique true point. So now let's look at it from the perspective of C and D. So if we look at a unique true point and a near false point for C, we want to find unique true points for CD, and then we want to change C from true to false to find the corresponding near false point. So we can pick this unique true point and its corresponding near false point, or this one, or this one. And if we look at D, we can pick this unique true point and its corresponding near false point, or that one, or that one. And so again, we'll just pick ones where we're able to reuse the unique true point so that we can collapse our 4 test cases into 3. Now, if we're really clever, we'll be going back thinking about what we did for AB and remembering what those test cases were so that we're trying to pick some for CD that possibly overlap what we picked for AB. So for example, this red test case, false, true, that's now part of the test set that we picked for AB as well as part of the test set that we picked for CD. So we've kind of further optimized our tests. We don't have to do that, right? They could all be separate. But if I can satisfy the test criterion with fewer tests by reusing tests that I have, that just seems like a smart thing to do. So that leaves us with these cells, these colored cells that we've selected. All right, so we chose for A and AB, we chose these 2 points. For B, we chose those 2. For C, we chose those. For D, we chose those. And instead of having a maximum of 2, 4, 6, 8 tests, if none of them overlapped, we've actually satisfied all of this with just 5 tests. So we've been a little bit, a little bit optimizing in our selection of tests, trying to save ourselves some work. And so from that, our test requirements, our set of tests to satisfy cut P and FP are these shaded cells. So hey, good for us. Cut P and FP finds all literal omission faults, which means it finds all of these too. Now, we still have a feasibility problem with cut P and FP because cut P and FP requires unique true points and near false points. And we've already seen that that's not always feasible. But when it is feasible, cut P and FP will find these. So MUT P and cut P and FP together, if they're feasible, will satisfy all possible classes of faults. So that sounds like a great combination of test criterion or test criteria. But is there a way to increase the feasibility so that we can address and properly test more predicates? Well, there is. We saw that MUT-P can be infeasible. CUT-P and FP can also be infeasible. So we can come up with this additional idea of multiple near false point coverage, MNFP, multiple near false point, yeah. So again, given a minimal representation for each clause or literal in each implicant, we're going to find near false points so that all of the clauses that are not in that implicant take on values true and false. Let's take a look at an example. So we want to look at each literal in each implicant, and we want to find near false points so that the clauses that aren't in the implicant take on values true and false. So for A in AB, we could choose perhaps these two near false points. And for B in AB, we could choose these two near false points, because these points cause C and D to both take on values that are true and false. And if we look at C, well, it turns out in C we're reusing the blue and the green. And when we look at D in CD, we're reusing the red and the purple. So we've done a pretty efficient job here, and we've found 4 test sets that satisfy multiple near false point coverage. And that leads us to combining all 3 of the previous things. So if we combine MUT-P and CUT-P and FP and MNFP together, then that's guaranteed to detect all the fault classes, even if any of them on their own are infeasible. So terrific. The problem is that's a lot of work, right? It's a lot of analysis work, and it can result in a lot of tests. So it's not really ideal. So the obvious, what's the word I'm looking for? Optimization. The obvious optimization of that is the even weirder name minimal mum-cut. And in minimal mum-cut, what we're going to do is say, is MUT-P feasible? And if MUT-P is feasible, then we'll use MUT-P and FP, right? Multiple unique true point and near false points. If MUT-P is not feasible, then is CUT-P feasible? And if it is, we'll use MUT-P and CUT-P. But if it's not, then we'll use MUT-P and multiple near false point coverage. And this process guarantees that if we carry out this flowchart, we're guaranteed to find all of the different fault types that we can have in DNF predicates. Oof. Is your head full? Because mine is.
Sound like that. If after the first diamond MUT-P is not feasible, how come the 2 off-ramps after that include MUT-P?
It's not feasible, but it's probably going to be, you're going to get tests that are feasible, right? So if we go back to if we think back to the MUT-P example, it'll take me longer to find the slide than to explain it.
I think I get it. Like still like use that to find what you can, but
yeah, well, exactly. We'll use what we can. We'll throw away what was infeasible, and we'll add on to it this additional approach.
Got it. Okay, thank you.
All right, so that takes us to the end for lecture today.